Tonight's journey follows a quiet, invisible drama. Two giant stars become two black holes. Their orbit tightens in darkness. Then, in a final moment, space itself trembles and carries the news across the universe. This is Space Dream's documentary. If these calm, cosmic stories help the mind slow down, please tap like and subscribe for more long-form space documentaries. Set notifications on and drift into the deep. In a quiet arm of a galaxy, gravity gathers two futures in the same cold cradle. The path to a pair of black holes begins as two massive stars form together and share a single orbit from the start. In that region, light fades inside dust. The cloud appears as a long dark filament with soft edges. Thin wisps overlap like smoke layered in still air. Within the filament, two knots thicken. Each knot is only slightly denser at first. The difference is enough. Gas drifts inward along shallow gradients. Dust grains move with it and deepen the shadow. A slow turn is present in the whole structure. Rotation keeps the collapse from staying centered. It spreads inward motion into a broad spiral. The filament does not fall into one point. It divides into two centers of fall. The scene is quiet and heavy. The first unlock is simple. A binary begins when gravity pulls inward, and rotation refuses a single landing. Around each growing core, a flattened sheet forms. It is not a solid disk. It is a cold, dense flow with a clear midplane and a softer halo. The sheet looks like a thin leaf of fog pressed into a plane. The edges are ragged. Streams feed it from above and below. The midplane becomes warmer than the outer layers. Heat tries to leak outward. Dust blocks most of it. Only a faint glow would escape from the least dense channels. The scale shift is gentle. Motions in a space smaller than a star's future radius decide the shape of an orbit that spans distances vast enough to hold both stars. The second unlock follows. A pair is not made by two separate births that happen to meet. The pair is carved from one rotating collapse that splits its own center. As the two cores gain mass, their pull reshapes the surrounding gas. The gravitational field is not round. It is stretched along the line between them. That stretching makes a shared valley in gravity. Gas drifts down the valley toward either core. Some gas misses both. It circles the pair as a wider ring. That outer ring stays dim and cold. It is a reservoir for later. Inside, the two inner flows remain distinct. The boundary between them is not a wall. It is a shifting saddle. Material crosses it when the balance tips. A calm, everyday image fits the geometry. Two raindrops form on the underside of the same leaf. Each drop grows from the same thin film. Surface tension keeps them separate. A slight tilt makes one draw more water. The same kind of small difference exists here. One core gains mass a little faster. The asymmetry persists. The orbit responds. The heavier core sits closer to the shared center of mass. The lighter one swings wider. The system settles into a steady rhythm. The period is slow at first. The distance between the cores can be about 100 million kilometers. That is like the span of a long sunlit arc across an interplanetary system. This number stays simple on purpose. The exact value varies widely. The idea is the point. A wide separation allows two large stars to grow without immediate contact. Over time, the pair tightens as gas drains away. Friction in the surrounding flow removes orbital energy. The third unlock arrives without urgency. The orbit is not a fixed track drawn once. It is a living balance set by how the cloud sheds heat and how the gas carries angular momentum outward. The word is simple. Angular momentum means spin that resists being stopped. A child's top keeps turning. A rotating cloud keeps its turn as it collapses. That matters because the turn must go somewhere. It is carried outward in the wider ring. It is stored in the orbit of the pair. The same physics that makes the sheet thin also keeps the two cores apart. The visual anchor deepens. The filament shows faint striations. They run along its length like combed fibers. Each fiber guides a slow stream into the cores. Where streams meet, the gas compresses. Compression warms it. Warmth tries to escape. Dust delays the escape. The delay makes collapse easier. The inner region becomes a nested structure. At the center, a growing protostar forms. Around it, a thick envelope remains. Around both protostars, the circumbinary ring turns as one. The whole scene is a set of layers. Each layer has a different density. Each density changes how quickly heat moves. A limit of observation sits here. The deepest parts cannot be seen directly because dust blocks the light. The central masses are inferred from motion and from the balance of heat. Even that inference has limits. Many different inner shapes can produce similar outer motions. Small errors in the early mass ratio can echo forward for millions of years. The fourth unlock is a quiet promise of later certainty. Even when the interior stays hidden, the orbit records what the cores become. The orbit is a clock that keeps time with gravity. Over a span of about 1 million years, the two protostars grow into full, massive stars. 1 million years is long, like a mountain slope slowly changing through countless storms. It is short compared with a galaxy's age. During that growth, the stars become bright and hot inside. Their surfaces are still wrapped in leftover gas for much of the time. When the envelopes finally thin, the pair appears as two luminous bodies on a shared path. The path is already shaped by earlier flows. The heavier star has the deeper well. The lighter star has the wider loop. The system is now set for the long burn of fusion. The section ends with a gentle forward turn. The next step is stability that hides a countdown. In that region, balance holds for a long time. The same balance also prepares the first collapse that follows. The new pair settles into a long quiet burn, and the most dramatic work hides beneath a calm surface. A massive star stays stable because inward gravity is matched by outward pressure from heat made in the core. In that region, each star has a clear center and a fading edge. The core is compact and bright. Around it, density falls outward in a smooth gradient. The outer layers look soft. They hold most of the volume. The surface can appear almost unchanged for long spans. Inside, a steady conversion takes place. Fusion means light nuclei join and release heat. The definition is short. The image is simple. Two small drops merge into one larger drop. A similar joining happens in the core but with nuclei and heat. The importance is quiet and absolute. Without that heat, the star contracts and changes its fate early. The main scene is a cutaway view through one star. A bright center glows like a deep ember. A paler mantle surrounds it. Faint striations show where energy moves outward. Some regions look smooth. Other regions look mottled in slow cells. The boundary between core and outer layers is not sharp. It is a zone where temperature and density slide from one regime to another. A first small unlock appears in the shape of balance. Gravity pulls inward everywhere. Pressure pushes outward everywhere. Neither wins for a long time. The result is a stable size and a stable brightness. At this distance, the surface light seems like the whole story. The interior tells a slower story in layers. Energy leaves the core and travels outward. It can move as radiation. It can move in bulk motion as convection. Radiation means energy travels as light through matter. Convection means hot material rises and cool material sinks. The definitions stay short. The examples stay grounded. Radiation resembles warmth, spreading through sunlit mist. Convection resembles warm air rising in a still valley at dawn. The importance returns to the orbit. A star that stays stable does not change the pair quickly. The orbit remains a clock that ticks with regularity. The second small unlock rests in the idea of time. A massive star can live about 10 million years. That span is like a brief wet season compared with the age of a continent. It is long enough for the orbit to settle. It is short enough to keep the future close. During those years, mass continues to shape everything. The heavier star burns fuel faster. Its core runs hotter. Pressure rises higher. The core stays smaller because gravity is stronger. The lighter companion burns more gently. Its core is less extreme. The difference is not dramatic at the surface at first. It is dramatic in the hidden centre. A slow checkpoint passes. The pair remain separate. The space between them stays clear. Their winds begin to matter. A wind is a flow of gas leaving the surface. It is not uniform. It can be denser near the equator. It can thin toward the poles. The flow forms a faint envelope around each star. Where the envelopes meet, a weak boundary appears. It is a place where pressures balance and streams bend. The main visual anchor deepens with this. Each star is surrounded by a faint curved wake of gas. The wake looks like a long veil. It narrows behind the motion. It broadens ahead of it. The shape is set by gravity and by the orbital path. A third small unlock appears in the meaning of stability. Stable does not mean still. It means the changes are slow and guided. The core slowly alters its composition. Hydrogen becomes helium. The center becomes denser. The temperature rises. Pressure adjusts. The star keeps its size within a limited range for a time. The surface stays calm. Under the surface, gradients steepen. In the core, the balance is delicate. A small rise in temperature can increase fusion strongly. The star responds by expanding slightly. Expansion lowers density. Fusion eases. The core settles again. The cycle is self-correcting within a range. A single concept holds this. Feedback is a response that pushes back against change. The definition is short. The example is plain. A pond level rises in rain and then spills through a low bank. The bank keeps the level from rising forever. The importance is direct. Feedback keeps the star from collapsing early. The narration drifts closer. At the edge of the core, a thin shell forms where fusion is weaker. Outside that shell, heat moves outward. The radiative zone can look like a clear gradient with no large swirls. Beyond it, convection may take over. Convection creates broad cells. Each cell is a slow rolling motion. The cell boundaries can be sharp in temperature. They can be soft in density. The surface can show a fine pattern. The pattern is not a set of points. It is a shifting mosaic of bright patches and darker lanes. The physical detail is concrete. Bright regions rise from below. Dark lanes mark cooler sinking flows. The scale shift is gentle. The motion of a single convective cell can be shorter than a day. The star's lifetime spans millions of years. Both rhythms coexist in the same sphere. A fourth small unlock appears in how the pair stays paired. Mass lost through winds can widen the orbit. Mass transfer can shrink it later. For now, the winds are modest compared with what comes. The orbit changes slowly. The clock remains steady. The wide view returns. Two bright bodies circle an unseen centre. Their light crosses the surrounding gas and is softened. Dust grains scatter some wavelengths. Other wavelengths pass through more easily. The environment is not empty. It is thin but present. The thin medium acts like a faint veil. Light behaves as a filtered glow. It carries hints about temperature and motion. The interior remains hidden. Here lies a limit of observation. The core cannot be seen directly because the outer layers absorb and scatter the escaping light. Only indirect clues exist. Surface brightness and colour can match more than one interior structure. A star with a slightly larger core can resemble a star with a slightly different mix of elements. The uncertainty is not a flaw of care. It is a boundary set by opacity and depth. The deeper the layer, the less direct the light that leaves it. The narration stays calm with that boundary. The fifth small unlock appears as a quiet reassurance. Even when the core stays unseen, gravity still sets firm constraints. Mass shapes luminosity. Mass shapes lifetime. Mass shapes the pace of change. In a binary, mass also shapes the future exchange between companions. The present stability is a preparation. The heavier star is already moving faster toward exhaustion. The lighter star follows. The orbit holds them together through the long burn. The section eases toward the next step. The calm surface continues for a time. Beneath it, layered burning begins to form and the countdown becomes more structured. The next section moves into those layers in the way mass writes an ending early. A bright surface can hide an interior that is already dividing into quiet layers. In massive stars, mass sets the pace and builds stacked burning shells that decide the ending long before collapse begins. In that region, the core stays small and dense. The pressure is high, the temperature climbs, the outer layers remain broad and comparatively light. A smooth gradient runs from center to edge. It is like a slow fade from bright to dim. The first small unlock sits in a simple change. When the core fuel shifts, the core tightens and heats, even if the surface hardly changes. The interior responds like a deep basin that slowly settles as sediment compacts. The settling is not visible from far away. It still changes the shape of what can happen next. A main visual scene forms as a cutaway through the star. The center glows brightest. Around it, a thin shell shines with a different color of heat. Farther out, another shell begins to form. Between shells, darker zones appear. Each zone is not empty. It is cooler and less active. The shells look like nested rings in a misty sphere. Their boundaries are soft. The edges ripple where flows mix. Light would scatter as it tries to leave. It would be absorbed and re-emitted many times. The second small unlock arrives with a definition that stays short. A burning shell is a thin layer where fusion occurs around an inert core. The image can stay plain. A coastline can hold several bands of wet sand after repeated tides. Each band marks a different waterline. In the star, each band marks a different fuel and a different depth. This matters because the core becomes a heavy anchor. The shells feed it. The core grows denser. The gravity at the center steepens. A single number can make the contrast feel real. The core temperature during steady burning can be about 20 million degrees. That is like the heat difference between a quiet volcanic chamber and the cool rock above it. The surface can still remain far cooler. The scale shift is gentle. The thickness of a burning shell can be small compared with the star's radius. The effect of that thin shell can steer the future of the whole star. A checkpoint passes in the form of time. The core changes composition. Hydrogen becomes helium. Helium piles up. The core does not burn helium at first. It compresses. Compression warms it. Warmth increases pressure. Pressure supports against gravity for a time. The balance continues. The surface brightness can stay steady. The orbit of the binary can keep its rhythm. The deeper story is hidden. A third, small unlock appears in the meaning of mass. More mass means a hotter core. A hotter core means faster burning. Faster burning means earlier transitions between fuels. This is not a dramatic leap. It is a steady slide. The star becomes a layered engine. Each layer has its own temperature range. Each layer has its own density. Each layer has its own way of moving energy outward. The visual anchor shifts closer again. Near the core boundary, a thin zone can appear where convection begins. Convection makes slow cells. The cells rise and sink. Their edges form curved seams. The seams drift like long cracks in drying mud but without sharp lines. The seams mark where heat is carried by motion instead of by light. The boundary can move over time. It can overshoot. It can mix material across layers. Mixing is a gentle word. It has a strong consequence. A small amount of mixing can carry fresh fuel inward. It can delay exhaustion. It can also blur the line between shells. The fourth small unlock comes from a careful limit. The interior cannot be read directly from the outside. The surface light is filtered by many layers. The wind carries away material, but it comes from the outer skin. Even the orbit only reveals total mass, not internal arrangement. Many different patterns of mixing can create nearly the same surface temperature and brightness. This is a limit of inference set by opacity and depth. The deeper the layer, the more indirect the evidence becomes. The star's hidden structure must be modelled. The model depends on assumptions about how layers stir. Those assumptions can be uncertain. The narration stays calm with that uncertainty. The picture remains useful because the broad pattern is robust. Massive stars tend to build shells. The core tends to grow heavier. The center tends to become more compact. The section moves forward through another checkpoint. Helium ignition begins when the core becomes hot enough. The ignition does not explode outward through the whole star. It begins in the center. It spreads through a region. The star adjusts its size. It can expand slightly. Expansion cools the core a little. The burn stabilizes. The surface can brighten. The outer layers can swell. The system remains quiet from afar. Inside, the layered story deepens. After helium, heavier fuels can ignite in sequence. Each stage is shorter than the one before. The shells become more numerous. The core becomes more inert between stages. The edges between shells can sharpen. Temperature gradients can steepen. Density gradients can steepen. The main visual scene returns with more detail. A thin, glowing ring of one fuel sits above a darker core. Above it, another ring burns. Above that, a broader zone carries heat outward. The star resembles a stratified cliff face seen in moonless light. Each stratum is distinct. Each stratum is laid down by different conditions. In a cliff, layers form over ages. In a star, layers form over a much shorter span. The analogy stays grounded. Both are records of changing environments. The fifth small unlock rests in why shells matter for the binary path. Shells set the size and the wind strength later. Shells set how easily the star expands toward the companion. Shells set when the core can no longer support itself. The orbit is still steady, but the future is being prepared in quiet layers. The scale shift softens outward again. The change in a shell thickness can be small. The effect can reach across a star's full radius. That effect can later reach across the distance between two stars. The section eases toward its next step. A layered interior is stable only while heat can push back. When a core reaches a fuel that cannot provide enough pressure, the balance slips. The next section moves into that slip and the first true collapse that follows. A star can look steady while its center quietly runs out of ways to hold itself up. Collapse begins when the core loses pressure support and gravity takes over faster than heat can respond. In that region, the core has become compact and heavy. The surrounding shells still burn in layers. They feed fresh ash inward. The core grows denser. Temperature rises. Pressure rises too, but the material changes its behavior. The first small unlock is simple and immediate. A core collapses not because gravity becomes stronger, but because support becomes weaker. The support comes from heat and from the structure of matter. When fuel is exhausted in the center, the heat source fades. The core contracts. Contraction heats it briefly. That heat cannot last. The core reaches a point where adding heat no longer provides enough pressure. A new term can appear once and stay short. Degeneracy pressure is resistance from crowded particles. It is like a packed crowd that cannot compress easily. In a core, crowded particles resist being squeezed. This matters because it delays collapse for a time. The delay is not permanent. When the core grows beyond what that pressure can hold, the balance breaks. The main visual anchor is a cutaway scene at the threshold. The core appears as a darker central sphere. Its edge is sharp compared with the earlier gradients. Around it, a thin, bright shell burns. Outside, a thicker shell glows more softly. The brightness is not uniform. It shows a ring-like structure where temperature peaks. Between shells, dim bands mark cooler zones. The boundary of the core is the key physical detail. It is a surface where density jumps steeply. The jump creates a steep pressure gradient. The gradient is a cliff, not a hill. The second small unlock arrives in the speed of events. Most of the star changes slowly. The final core collapse can happen in about 1 second. That is like a single heartbeat compared with millions of years of quiet burning. The scale shift is gentle. A process that took ages suddenly compresses into a moment. The outer layers do not react immediately. They are far away in distance and in time response. The core falls inward. Material accelerates. Density rises. The The core becomes more opaque, light cannot escape, heat cannot flow out fast enough. The collapse is driven by gravity and by the inability to communicate pressure outward. A calm, everyday analogy can hold the shape. A sand pile stands while grains support each other. When a thin layer at the base is removed, the pile slumps suddenly. The collapse is not a choice. It is a response to lost support. In the star, the lost support is in the centre. The surrounding shells keep burning for a moment. They are like a lamp still lit while the foundation below shifts. The third small unlock appears in what collapses and what does not. Only the core falls quickly at first. The envelope remains almost in place. The collapse creates a shock wave later, but the early stage is inward. The core crosses a threshold where ordinary pressure laws change. Crowding of particles becomes extreme. Neutrinos begin to carry away energy. The term can stay light and defined. Neutrinos are nearly massless particles that pass through matter. They matter because they remove energy from deep layers. Their escape cools the core. Cooling reduces pressure. Reduced pressure speeds collapse. The sequence is calm but firm. The core shrinks. Density rises. Particles pack tighter. Energy leaks away in forms that do not easily heat the outer layers. The main visual scene shifts slightly. The core edge moves inward. The bright shell above it is left behind at first. It then follows. Layers compress like soft fabric gathered toward a pinched centre. The fabric image stays physical. The folds grow tighter. The spacing between folds decreases. The thickness of each shell changes. The gradients steepen. The outer layers remain huge and slow. The inner region becomes small and fast. Another checkpoint passes. At some point the inner core can rebound slightly. A shock can form. The shock moves outward into infalling material. The shock can stall. It can revive. The details can vary across masses. The key idea remains. Collapse is not always a clean bounce. It can be a struggle between infall and outward push. Here lies a limit of intuition and a limit of modelling. The core is hidden behind extreme density. Light cannot report from the centre. The behaviour depends on microphysics under conditions not reproduced elsewhere. Even careful calculations can disagree on how the shock evolves. The uncertainty is specific. It comes from how energy is transferred between particles. It comes from how neutrinos deposit energy in surrounding layers. It comes from how rotation and magnetic fields, if present, shape flow. Those factors cannot be read directly from the surface before collapse. The outer appearance can be similar for different interiors. This is not a mystery posed for suspense. It is a boundary of inference set by opacity and complexity. The fourth small unlock arrives in what survives the collapse. A compact remnant forms. It can be a neutron star. It can be a black hole. The outcome depends on core mass and on how much material falls back. The narration stays gentle. In that region, the remnant is defined by gravity and by a boundary. For a black hole, the boundary is the event horizon. An event horizon is a surface beyond which escape is impossible. The definition stays short. The imagery stays quiet. It resembles a region where paths curve inward so steeply that outward routes no longer exist. A physical detail can anchor it. The surrounding space can have an inner shadow. Outside that shadow, a thin ring of hot gas can orbit briefly. The ring is not stable for long. It can thicken. It can break. It can feed inward. The fifth small unlock ties back to the binary path. The first collapse changes the mass balance. It can kick the orbit. It can widen it. It can tilt it. Yet the pair can remain bound if enough mass stays, and if the kick is gentle. Even when the light from the explosion fades, the orbit keeps a record. The system becomes a mixed pair. One compact object and one massive star remain. The scale shift softens outward again. A boundary smaller than a star's diameter shapes an orbit that spans hundreds of millions of kilometers. The section eases into the next step. After the first collapse mass transfer and winds become stronger influences. The next section moves into how outer layers peel away, and how the binary begins to tighten toward a darker future. After the first collapse, the remaining star begins to shed its outer layers in ways that quietly reshape the orbit. The binary tightens or loosens because mass loss and mass transfer change how gravity is shared between the two bodies. At this distance, the scene is not an explosion. It is a slow peeling and a slow drift of gas. The surviving star is still bright. Its outer envelope is extended. Its density fades outward in a gentle gradient. Around it, a thin wind forms a translucent shell. The shell is not uniform. It has streaks and gaps. The gaps are lower density channels. Light behaves as a softened glow through that uneven veil. The compact remnant remains dark by itself. Its presence is felt through motion. The first small unlock appears immediately in the meaning of distance. The orbit can widen when mass leaves the system because the total pull weakens. It can tighten when mass moves from the star toward the remnant because energy is drained from the orbit. These two trends can coexist in different phases. The binary does not march in one direction. It adjusts like a balance that keeps being nudged. The main visual anchor is a broad spiral of gas around the pair. It is faint and wide. It resembles a drifting ribbon in slow water. The ribbon is brightest along a curved edge where the flow compresses. Behind that edge, the gas thins into a tail. The tail is colder and more diffuse. The spiral wraps around the system and blends into the surrounding medium. The physical detail that matters is the boundary of flow. Close to the star, the wind is fast and rarefied. Near the remnant, the flow can thicken into a wake. The wake has a curved shock, like a soft bow in the gas. The bow is not sharp, it is a smooth arc where density rises. The second small unlock comes from a single concept that stays simple. Roche lobe is the region where material stays bound to one object. The definition is short. The image is calm. Two shallow bowls touch at a narrow saddle between them. Water placed near the saddle can slip into either bowl. In the binary, gravity shapes two bowls. The saddle is the point where balance is delicate. This matters because an expanded star can spill material across the saddle. The star does not need to explode to do this. It only needs to swell so its outer layers cross that boundary. The swell can happen as the star evolves and its envelope loosens. The outer layers are light compared with the core. They can drift outward with modest energy. When the envelope crosses, the saddle gas flows toward the remnant. The flow forms a stream. The stream is the clearest shape in the scene. It is narrow near its origin. It widens as it curves. It carries angular momentum. It does not fall straight in. It wraps into a ring around the remnant. The ring is not a rigid circle. It is a thickened loop with a brighter inner edge and a dimmer outer edge. The brighter edge marks where the flow compresses and heats. The third small unlock rests in how the orbit pays for that stream. When gas moves inward, it carries energy and angular momentum away from the orbit. The orbit responds by shrinking. The change is often gradual. It can be dramatic over long time. A single number can keep the scale safe. The orbital period can shrink to about 1 day. That is like the turning of a planet under a steady sunrise. This number is only a marker of closeness. The important idea is that the pair can move from wide separation to tight companionship. The scale shift is gentle. A stream only a few star diameters wide can over time reshape an orbit that spans tens of millions of kilometers. The narration moves through checkpoints. First wind loss dominates. The star loses mass into space. The orbit tends to widen. Second expansion brings the envelope near the saddle. The stream begins. The orbit begins to shrink. Third, the flow becomes unstable. The stream can thicken. It can wrap into a temporary disk. The disk can flicker in density. It can throb in thickness. The bright inner edge can move inward and outward. The gas does not behave like a clean line. It behaves like a living fluid. A fourth small unlock appears in what is removed and what remains. Mass transfer can strip the envelope. The star becomes more compact. Its surface temperature can rise. Its wind can change character. The core becomes more exposed. The star can become a helium-rich object with a thinner envelope. The remnant gains mass. It can grow from a neutron star to a black hole if enough matter settles. The boundary between these outcomes depends on how much mass is added and how quickly. The section holds a calm limit of understanding. The flow is three-dimensional. It is turbulent. It can form clumps. It can form gaps. Its exact behaviour depends on cooling and on rotation. Those details cannot be read directly from far away without ambiguity. Many different flow patterns can produce similar overall orbital changes. Even with careful modelling, the thickness of the stream and the efficiency of angular momentum loss remain uncertain. The uncertainty is specific. It comes from how gas shocks and cools. It comes from how clumps interact with the disk. It comes from how much material escapes instead of settling. This boundary does not weaken the broad picture. It only softens the precision of predictions. The fifth small unlock returns to the visual anchor of the spiral ribbon. Over time, much of the transferred gas does not remain. Some is flung outward. It forms a broader circumbinary structure. That structure can be a faint ring. Its inner edge can be sharp because it is carved by the orbit. Its outer edge can be diffused because it blends into the surrounding medium. The ring acts like a memory of transfer. It stores angular momentum. It stores heat briefly. Then it cools and fades. The system becomes quieter again. The orbit has changed. One object is compact and dark. The other is stripped and smaller. The pair is now closer. The scene remains free of instruments. Only gravity and gas shape the story. The section eases toward the next step. A closer orbit sets the stage for a second collapse. The next section moves into the companion's final exhaustion, and the moment when the binary becomes two compact remnants on a shared track. A tightened orbit can hold a quiet certainty that the second collapse is approaching. The binary becomes two compact remnants when the stripped companion exhausts its core and falls inward, leaving gravity to define the pair. In that region, the companion is smaller than before. Its surface is hotter. Its envelope is thin. The interior is layered and dense. A faint wind still leaves the surface. The wind is weaker and faster. It forms a narrow sheath that fades into the dark. The compact companion from the first collapse remains close. Its gravity shapes nearby gas into a curved wake. The first small unlock arrives in a plane shift. When the envelope is mostly gone, the core dominates the star's behaviour. The remaining layers act like a thin skin over a heavy centre. The skin can expand and contract. The centre follows its own timeline. The key timeline is set by burning heavier fuels. Those fuels are spent quickly. The star changes faster now. The main visual anchor is a close cutaway of the stripped star beside the compact remnant. The stripped star shows a bright inner glow beneath a pale surface. Its outer boundary is clean. Around it, a faint halo of escaping gas forms a smooth gradient. Between the two bodies, the space is not empty. A low-density bridge of gas curves toward the remnant. It does not touch like a solid link. It is a soft flow. It forms a thin arc. The arc has a brighter edge where density rises. Behind that edge, the flow thins and cools. The second small unlock comes from a term that stays short. Fallback is material that fails to escape and returns inward. The image stays grounded. A tossed handful of dry sand can form a brief arc, then settle back. In the star, some layers are lifted during collapse. Some do not reach freedom. They return. This matters because returned mass can push a remnant past a threshold. The threshold decides whether a neutron star remains or a black hole forms. The story stays calm. The core continues to densify. Pressure from heat becomes less effective. Degeneracy pressure can hold for a while. It is the resistance of crowded particles. The support is strong but limited. If the core is heavy enough, the support yields. Collapse begins. The collapse is fast compared with the star's life. The orbit continues its quiet cycle until it does not. A single number can anchor the scale. The final collapse can unfold in about 1 second. That is like a single breath compared with the long, quiet orbit that came before. The scale shift is gentle and wide. Millions of years of burning compress into a moment of inward motion. At this distance, light behaves as a delayed messenger. The outer layers do not know at first. The center falls, density rises, temperature spikes. Neutrinos carry energy away. The escaping energy does not brighten the outer space in a simple way. Much of it leaves without heating the visible layers. The third small unlock appears in what the orbit feels. The collapse changes mass distribution quickly. If some mass is ejected, the orbit can loosen. If mass falls back, the orbit can tighten slightly. The final result depends on how much stays. The compact remnant forms at the center of the collapse. If it becomes a black hole, an event horizon forms. It is a boundary beyond which escape is impossible. The boundary is not a surface of matter. It is a line in space that marks a limit of paths. A physical detail can hold the image. Around the new black hole nearby, gas can form a brief ring. The ring is thick and uneven. Its inner edge is sharper. Its outer edge is softer. The ring can glow faintly as it heats by friction. The glow is short-lived if the gas supply is thin. The binary now holds two compact objects. Their separation can be small compared with the earlier star sizes. The orbit becomes cleaner. There is less extended gas to blur it. The pair can be dark except for thin residual flow. The main visual anchor shifts outward. Two invisible wells circle an unseen center. A faint ring of dust far outside turns with them. It is a pale ellipse. Its inner edge has a slight gap carved by the orbit. The gap is a physical signature. It is a place where particles are repeatedly disturbed and cleared. The fourth small unlock rests in the meaning of invisibility. The objects can be unseen in light. Their gravity remains measurable through motion and through later waves. The system becomes a quiet machine of curvature. It loses energy slowly. The loss is not by wind now. It is by gravitational waves later. That is the path ahead. Before that, a limit of observation and a limit of modelling appears again. The exact mass of each remnant depends on how much material falls back. That fallback is hard to predict because it depends on the explosion energy and on the star's structure. The structure was hidden by opacity. The explosion is complex. Even in models, small changes in mixing can alter how much returns. The uncertainty is specific. It lies in the distribution of density in the outer core and in the timing of the shock. The orbit after collapse can also be uncertain. A small kick can tilt the plane. The kick comes from asymmetry in ejection. The asymmetry cannot be inferred cleanly beforehand. This boundary remains gentle. It does not erase the large story. Two compact remnants can still remain bound in many cases. The fifth small unlock comes as a calm consequence. If the pair stays bound, the future is long but directed. The orbit becomes the main reservoir of energy. Over time, the pair radiates that energy away as space-time ripples. The separation shrinks, the period shortens, the motion speeds up. The scene stays quiet and clean. There is little gas left to paint it with light. The physics becomes more geometric. A scale shift settles outward again. A boundary only a few tens of kilometers across defines one remnant. The orbit spans millions of kilometers. The galaxy holds it all as a tiny point. The section eases into the next step with soft certainty. Two dark masses now circle each other. The next section moves into what a black hole is as a boundary, and how the orbit can exist with almost no light. Two black holes can share an orbit without showing any surface at all. The reality of a black hole is a boundary in space that shapes motion, not a visible object with edges of matter. In that region, the pair is quiet. There is little gas left from earlier phases. The background star field is thin. The darkness of each black hole is not a colour. It is an absence of escaping light from within a certain radius. The first small unlock is immediate. A black hole is defined by an event horizon which is the point of no return for outward paths. The definition stays short. The image can stay calm. It is like a river that narrows toward a waterfall. Far upstream paddling can move against the flow. Closer in the current becomes too strong. Beyond a line, even the strongest stroke cannot climb back. In space, that line is not water. It is the geometry of space and time. It matters because the boundary changes what orbits can exist and what signals can be produced. The main visual anchor is a slow wide view of the binary against faint dust. The dust forms a thin, uneven ring far from the pair. The ring is an ellipse. Its inner edge shows a shallow gap. The gap is carved by repeated gravitational stirring. The dust grains move in smooth paths. Near the black holes, the dust is absent. The inner region is clear because any stray gas has been pulled inward or flung outward long ago. The black holes themselves have no surfaces, yet their gravity has structure. The gravitational field has steep gradients close in. Farther out, it becomes gentle. The second small unlock comes from a new term used once. Schwarzschild radius is the size of the event horizon for a non-spinning black hole. The definition stays short. It is the radius where escape becomes impossible. An everyday comparison can keep the number grounded. For a black hole with about 10 times the mass of the Sun, the horizon size is about 30 kilometers. That is like the length of a long bridge across a wide river. The number is not a precision claim. It is a scale marker. The scale shift is quiet and large. A boundary measured in tens of kilometers controls an orbit that spans millions of kilometers. That orbit sits inside a galaxy that spans tens of thousands of light years. The mind can rest on the contrast. The narration moves closer. At a modest distance from a black hole stable, orbits exist. The paths are smooth. They can be nearly circular. They can also be slightly elliptical. Closer in space, curves more strongly. Orbits precess. Precession means the orbit's closest point shifts each cycle. The definition stays short. The image is calm. It is like a drawn oval that slowly rotates on a sheet of paper without changing its size. The importance is direct. Precession changes how two black holes approach each other over time. It alters the rhythm of their motion. The third small unlock appears in why an orbit can persist at all. The pair does not fall together immediately because angular momentum keeps them moving sideways. Gravity bends their paths inward. The sideways motion carries them past the centre. The result is continuous falling and continuous missing. Each orbit is a balance between inward pull and sideways speed. In that region, the balance is clean. There is no solid surface to collide with. There is only curvature and motion. The physical details remain concrete. The region around each black hole has an invisible slope. The slope is steeper closer in. The slope is shallower farther out. The slope can be imagined through a faint pattern in surrounding dust. Dust closer in would orbit faster. Dust farther out would orbit slower. The difference creates shear. Shear means nearby layers slide past each other at different speeds. The definition stays short. The image is gentle. It is like the centre of a slow whirlpool turning faster than the outer water. This matters because shear can heat gas if any remains. Heated gas can glow briefly. The glow would trace the ring like structure around the black hole. The ring would be brightest at its inner edge. The ring would fade outward. The main visual anchor returns to the cleared central cavity. The dust ring far away remains. It slowly twists. The twist is subtle. It comes from the gravitational tug of the binary. Each pass adds a tiny disturbance. Over long spans, the ring can develop faint clumps. The clumps are not stable. They stretch and smear. The smear is a signature of differential motion. The fourth small unlock sits in a gentle limit. A black hole cannot be seen directly by light if no gas is present to glow. Its mass and its orbit must be inferred from how nearby matter moves. That inference has limits. A sparse dust ring only samples the gravitational field at its own distance. It cannot reveal the exact horizon size. It cannot reveal the exact spin. Many combinations of mass and distance can produce similar outer motions. The uncertainty is specific. It comes from the lack of traces close to the black holes. It comes from the blending of signals from both objects. Even if a faint glow appears, the glow depends on gas supply, which is uncertain. The mind can rest with that boundary. The large-scale picture remains firm. The binary exists because gravity permits closed paths. The binary evolves because energy can leave the system in subtle ways. For now, the pair loses energy slowly by gravitational waves. That loss is tiny at wide separation. It grows as the orbit tightens. The fifth small unlock appears in the idea of clean silence. In an almost empty region, the only long-term drain is the shape of space-time itself. Nothing needs to touch. Nothing needs to shine. The orbit still changes. The change is gradual. The period shortens. The speed rises. The separation shrinks. The story remains calm because the timescales are vast at first. Millions of years can pass with little visible difference, yet the direction is set. The binary is like two smooth stones circling on a taut fabric. The fabric dips under their weight. The stones follow the curve. The dip is not a solid thing. It is the geometry. The section eases toward the next step. The next section moves into the way energy leaves, as travelling distortions and how a slow orbit becomes a measurable wave pattern, without needing any light. A wide orbit can look eternal, yet it quietly leaks energy into the emptiness around it. Gravitational waves carry away orbital energy as travelling distortions in space and time, and the binary slowly tightens because of that loss. In that region, nothing needs to shine. The pair can be almost invisible. The only change is in geometry and rhythm. The first small unlock is immediate and plain. A gravitational wave is a ripple in space-time that moves outward at the speed of light. The definition stays short. The image can stay gentle. A stretched sheet can carry a slow pulse when it is tapped. The sheet does not travel. The pulse does. In space, the sheet is not material. It is the measure of distance itself. This matters because distance is what an orbit constantly negotiates. When distance becomes a wave, the orbit can pay energy into the wave without friction and without contact. The main visual anchor is a quiet map of star fields seen from far away. Around the binary, faint concentric shells spread outward. They are not light. They are a pattern of slightly stretched and slightly squeezed spacing between points. The shells are widely spaced at first. They drift outward like long swells across a deep ocean at night. The physical detail is subtle but concrete. Each shell has a front edge where spacing is slightly larger. Behind it, spacing is slightly smaller. The pattern alternates. The alternation is the wave. The second small unlock arrives in why a circular orbit emits at all. A perfectly still mass does not radiate waves. A changing mass pattern does. Two masses in orbit create a changing quadrupole. Quadrupole means a pattern with two directions stretched and two directions squeezed. The definition stays short. The example stays grounded. A soft rubber ring squeezed in one direction bulges in the other. As the squeeze rotates, the bulge rotates too. In the binary, the squeeze is the gravitational field. It rotates with the orbit. This matters because the rotation makes a repeating wave. The wave frequency tracks the orbit frequency. A third small unlock comes from the sense of weakness. The wave is extremely small in amplitude at great distance. It is not a tide that lifts dust. It is a fractional change in distance. It can pass through gas and dust with almost no interaction. The orbit still feels it because the wave carries away energy. Energy loss means the orbit shrinks. The shrink is slow at first. It is steady. The scene moves through checkpoints. First, the binary is wide. The wave is weak. Many millions of years can pass with little change. Second, the orbit becomes tighter. The wave grows stronger. The energy loss per orbit increases. Third, the tightening feeds itself. A smaller orbit means higher speed. Higher speed means a stronger changing quadrupole. Stronger change means stronger waves. The loop is calm and directed. A single number can anchor the change. At a separation of about 1 million kilometers, the orbital period can be about 1 hour. That is like the turning of a short hand around a clock face. The number is not universal. It is a safe scale marker. It shows how close the pair can become before the final rush. The scale shift is gentle. A boundary of tens of kilometers defines each horizon. An orbit of 1,000,000 kilometers defines the wave period. The wave then spreads across thousands of light years without fading in shape, only in strength. The main visual anchor shifts inward. The two black holes circle faster. The empty space between them feels clean. There is no surface. There is only curvature and motion. If any thin gas remains, it forms a faint ring that cannot keep up. It is disturbed and flung outward. The ring becomes a broken arc. The arc is not stable. It becomes a smear. The smear marks where shear is strong. Shear means nearby paths slide at different speeds. The definition stays short. The image stays soft. It is like two lanes of a slow river moving past each other and forming a line of foam. This matters because it shows how little matter is needed for patterns to appear, even when the wave story needs none. A fourth small unlock appears in how the wave is encoded. The wave has two polarizations. That means it can stretch space in two perpendicular patterns. The definition stays short. The example stays calm. A circle drawn on soft clay can become an oval in one direction, then an oval in the other. The circle returns and repeats. This matters because the passing wave alternately lengthens and shortens distances along different directions. The alternation is the signal. The wavefront expands outward. Its energy spreads over a growing sphere. Its amplitude falls with distance. The pattern remains coherent. The fifth small unlock rests in what cannot be known from the wave alone. A distant wave can reveal the combination of masses and the distance scale, but not every detail uniquely. Different mass pairs can produce similar wave shapes if their distances are different. Spin can change the phase. Eccentricity can add harmonics. Those effects can be subtle. Here lies a limit of observation and a limit of inference. The wave is a tiny strain. It must be separated from noise and from other waves. Even in ideal modelling, degeneracies remain. Degeneracy here means different parameters can mimic each other. The definition stays short. The image stays grounded. Two different recipes can yield the same flavour if sweetness and acidity trade places. This matters because certainty comes in ranges, not in perfect single values. The narration stays calm with that. The overall story does not depend on perfect numbers. It depends on the direction of change. The orbit loses energy. The loss accelerates as the orbit tightens. The wave becomes faster and stronger. The period shortens. The spacing between wave crests shrinks. The main visual anchor returns to the expanding shells. Far away, the shells are almost flat. They sweep through a starfield like a gentle pressure front through high clouds. Near the source, the shells are tightly packed. They emerge like ripples close to a dropped pebble. The scale shift is soothing. Near the pair, time is measured in seconds and minutes. Far from the pair, the wave takes thousands of years to cross large distances. The section eases toward the next step. As the orbit tightens, the wave rhythm rises into a smooth chirp. The next section moves into that chirp, and the way the final spiral becomes a clean, measurable pattern in time. A quiet orbit becomes a steadily rising rhythm as two black holes draw closer. The chirp is the smooth increase in wave frequency and strength that comes from a tightening spiral. In that region, the pair circles in near darkness. Only geometry carries the story outward. The first small unlock arrives at once. A chirp is a signal whose pitch rises with time because the orbit speeds up. The definition stays short. The image stays calm. A rolling marble on a shallow bowl circles slowly, then faster as it drops lower. The bowl does not chase the marble. The shape guides the speed. This matters because the rising rhythm encodes the masses and the shrinking separation. The main visual anchor is a close view of the orbit traced not by light, but by faint markers in surrounding dust. A thin haze lies far outside. Inside, the space is clean. Two dark centres sweep around each other. Around the pair, the wavefront forms a tight spiral pattern in the spacing of the surrounding region. The pattern is not a glowing line. It is an alternating stretch and squeeze. The physical detail is clear. The spiral arms are closer together each turn. The spacing decreases as the orbit tightens. The second small unlock comes from a simple concept. Phase is the position within a repeating cycle. The definition stays short. The example stays grounded. A lighthouse beam sweeps the horizon and marks where the cycle is. In the wave phase marks where the stretch and squeeze are in time. This matters because a long series of phases carries precise information about the orbit's history. The narration moves through checkpoints. At first, the orbit is wide enough that the chirp is slow. The wave crests are far apart. The change from one orbit to the next is tiny. Over time, the crests compress. The rhythm rises. The amplitude grows. The change becomes noticeable within a shorter span. The shift is gentle and continuous. A single number can anchor the feeling. Near the late Inspiral, the wave frequency can reach about 100 cycles per second. That is like a fast humming vibration in a thin wire. The number is only a scale marker. It helps place the chirp within a range that is neither too slow nor too fast to imagine. The scale shift is soothing. 100 cycles per second is a human-sized rhythm. The system that creates it spans millions of kilometers and contains masses larger than stars. The narration draws closer to the moving geometry. As the black holes orbit, the separation shrinks each cycle. The orbit is still smooth. It is nearly circular in many cases. Any earlier eccentricity has often been damped by wave emission. The spiral is not a sudden plunge. It is a gradual tightening that accelerates only near the end. The third small unlock appears in why the chirp rises. A smaller orbit means higher orbital speed. Higher speed means a stronger changing quadrupole. Stronger change means stronger waves. Stronger waves remove more energy. The feedback is calm but firm. Each loop takes less time. Each loop radiates more. The wave train becomes denser. The wave crest spacing shortens. The main visual anchor shifts to the pattern at distance. The outward moving shells seen earlier are now packed closer near the source. Far away, the shells are still wide. Near the source, they look like fine ripples in a pond close to where a breeze touches the surface. The ripples are not water. The similarity is in spacing and smoothness. The fourth small unlock comes from how clean the chirp can be. The waveform is dominated by the orbital motion, not by gas, not by friction, not by magnetic storms. The signal is a story of gravity alone. That is why it can be modelled with high confidence in many parts. The confidence has a boundary. The final moments approach conditions where gravity is extremely strong. Approximations begin to fail. Here lies a limit of modelling and a limit of intuition. Weak field formulas work well when the orbit is wide. They become less accurate as the separation shrinks. The exact phase evolution near the end can depend on spin and on higher order effects. Those effects can be subtle yet important. This boundary is specific. It is a limit of calculation methods and numerical resolution. It is also a limit of mental pictures. Orbits near the last stable region cannot be pictured as simple circles on a flat plane. Space is too curved. Time is too warped. The narration stays quiet with that boundary. The waveform remains meaningful because it still rises smoothly and predictably in a broad sense. The fifth small unlock arrives in what the chirp reveals even with uncertainty. The early part of the chirp sets the mass scale through its slow evolution. The later part tightens constraints through its rapid rise. The full arc tells how quickly energy is lost. It tells how close the pair must be. It tells how massive the system is. The story can stay physical. The wave is an alternating stretch and squeeze. That stretch and squeeze passes through empty space. It does not need matter to ride on. At a distance, the effect on any two free points is tiny. Their separation changes by a small fraction. The fraction is so small that direct sensing is difficult. That is a limit of observation. The strain can be smaller than the size of an atomic nucleus over a distance as large as a continent. The statement is a scale comparison, not a measurement claim here. It shows why the signal is hard to catch. The limitation is in sensitivity and in separating the signal from other disturbances. Even in an ideal setting, many chirps overlap across the universe. Distinguishing one event requires clarity of timing and pattern. The chirp helps because its rise is distinctive, yet the very small amplitude remains the core challenge. The main visual anchor returns to the spiral arms of the wave near the source. Each new arm is laid down faster than the last. The arms tighten, the orbit speeds up. The black holes approach the point where separate paths no longer remain stable. The section eases toward the next step without suspense. The chirp continues to rise. It approaches a final transition where the inspiral ends and the merger begins. The next section moves into that transition, and the moment when ordinary orbital language yields to a single merged geometry. Near the end of Inspiral, the orbit becomes so tight that the idea of two separate paths begins to blur. The merger begins when stable orbits disappear, and the two horizons reshape into a single common boundary. In that region, the motion is fast. The space between the black holes is small. The wave rhythm is high. The scene remains dark in light. It is bright in geometry. The first small unlock is immediate. The Inspiral ends because the last stable orbit is reached, not because something strikes a surface. The term can stay simple. The last stable orbit is the smallest path that remains steady. Below it, a small disturbance leads to plunge. The image stays calm. A ball can circle inside a shallow bowl. As the bowl steepens, there is a point where circling cannot stay smooth. The ball slides inward no matter how it is nudged. This matters because the change from inspiral to merger is a shift in stability, not a sudden new force. The main visual anchor is a close view of two shadows in curvature. Each black hole has an event horizon. The horizons are not visible walls. They are boundaries where outward paths end. As the pair tightens, the horizons develop a stretched shape. They are no longer perfect spheres. Each is slightly elongated toward the other. The space between them narrows into a throat-like region. The throat is not a tunnel of matter. It is a region where curvature is strong and changing. The physical detail is clear. A thin ridge of curvature forms between the horizons. The ridge thickens. The ridge becomes a shared envelope. The second small unlock comes from a short term used once. Common horizon is the single boundary that encloses both masses. The definition stays short. The image stays grounded. Two soap bubbles touch, and then become one larger bubble when the film rearranges. The bubbles are not the same as horizons, but the idea of separate boundaries becoming one is close. This matters because the formation of a common horizon marks the moment when two objects become one system. The wave signal responds immediately. The chirp reaches a peak and then changes character. The waveform is no longer a steady rise. It becomes a brief complex burst. The narration moves through checkpoints. First, the orbit still exists, but it is unstable. Second, the plunge begins. The separation shrinks quickly. Third, the horizons form a common boundary. Fourth, the merged shape settles. A single number can anchor the time. The strongest part of the merger can unfold in about 1/10 of a second. That is like the blink of an eye compared with the long inspiral before it. The scale shift is gentle. Millions of years of slow tightening lead to a fraction of a second of rapid change. The wavefront around the system is now tightly packed. The crests are close in time. The amplitude is at its strongest. The main visual anchor shifts outward to the wave pattern leaving the source. The wavefront is no longer a clean spiral. It becomes a set of compressed shells with slight asymmetry. The shells expand outward. Each shell carries a record of the changing shape of the source. The shells have a front edge where space is stretched. Behind it, space is squeezed. The alternation continues. The pattern is more complex for a moment. The third small unlock appears in what sets the final mass. The merged black hole is slightly less than the sum of the two original masses. The difference leaves us gravitational waves. The idea can stay simple. Some orbital energy becomes travelling curvature. The mass of the remnant reflects that loss. No light is needed. No matter is required. Geometry alone carries away the energy. The narration stays calm and precise. The remnant is not instantly quiet. It is distorted. It rings. Ringdown is the settling of the horizon shape through damped oscillations. The definition stays short. It is the fading vibration of the new black hole's geometry. The image remains gentle. A struck bell cannot be used here because it suggests crafted objects. A better everyday image is a pond surface after a stone falls. The ripples spread and fade. The water returns to stillness. In the merger, the horizon shape ripples and then smooths. This matters because the ringdown frequency depends on the remnant's mass and spin. The main visual anchor returns inward. The new horizon is larger. It is more symmetric than the stretch pair. Around it, space has a deeper central curvature. If any thin gas remains, it forms a faint ring far outside. The ring is disturbed by the burst. It can wobble slightly. It then returns to a smooth ellipse. The inner edge of that ring stays carved. It is a quiet reminder of the binary history. The fourth small unlock is a gentle limit. The merger happens in a regime where gravity is strongly nonlinear. Simple approximations fail. Intuition based on weak curvature fails. Predicting the exact waveform requires detailed numerical solutions. Those solutions have limits. They depend on resolution and on assumptions about spins and orientations. Even with strong models, there can be degeneracies. Different combinations of mass ratio and spin can mimic each other in parts of the signal. This is a limit of inference from waveform shape alone. It is also a limit set by how much of the signal is cleanly separated from background disturbances. The narration holds that boundary softly. The broad story remains stable. The Inspiral rises. The merger peaks. The ringdown fades. The fifth small unlock arrives in what the merger leaves behind in space. The wavefront continues outward. It expands as a growing sphere. Its amplitude decreases with distance. Its pattern remains. In that region far away, the wave is a faint alternating stretch and squeeze that passes through dust and gas almost without effect. The galaxy does not react as a whole. The wave is too small, yet the wave is a measurable imprint of the event. The scale shift settles outward. A tenth of a second near the source becomes thousands of years of travel across a galaxy. The wave carries the timing intact. The section eases toward the next step. After the merger, the remnant enters a clean ringdown. The next section moves into that settling, and the way a single black hole becomes smooth again, while the wave signal fades into quiet. After the peak, the universe grows quiet again as the merged black hole smooths itself. Ringdown is the fading set of oscillations that carry away the last distortions of the new horizon. In that region, the wave signal changes from a rising chirp into a short, damped tone. The first small unlock is immediate. Ringdown happens because the merger leaves a distorted horizon that cannot stay misshapen. The horizon is a boundary. It settles toward a stable shape. The settling radiates away the remaining asymmetry as gravitational waves. A term can appear once and stay short. Quasi-normal modes are the natural vibration patterns of the horizon. The definition stays short. They are the preferred ways the new black hole can oscillate. The image can remain calm. A tall column of mist can sway after a gust, then return upright as the swaying fades. The mist does not have a rigid frame. The shape still prefers a smooth center. This matters because the fading pattern encodes the mass and spin of the remnant. The main visual anchor is a close view of the new horizon as a dark sphere in curvature. Around it, a faint halo of residual gas lies far out. The gas is thin and uneven. It forms a broken ring that slowly rounds out. The horizon itself has a subtle physical detail. Its geometry can be slightly bulged around the equator if it spins. The bulge is not a surface ridge. It is a difference in how space curves near different latitudes. Close in the curvature, gradients are steep. Farther out they soften. The second small unlock arrives in how damping works. The oscillations fade because energy is carried away by waves. Damping means the amplitude decreases over time. The definition stays short. The example is grounded. A ripple in a quiet pond becomes smaller with each outward ring, until the surface looks still. In ringdown, the ripple is in geometry. The outward travelling wavefront carries the oscillation away. The horizon becomes smoother. The wave becomes weaker with distance. The narration moves through checkpoints. First, the merger creates a complex burst. Second, the system enters a simpler oscillation pattern. Third, the pattern fades into near silence. The transition is gentle. It is not a sharp stop. The waveform becomes a clean decaying rhythm. A single number can anchor the timescale. The main ringdown can fade in about 1/10 of a second. That is like a brief exhale compared with the long Inspiral. The scale shift is soothing. 1/10 of a second near the source becomes thousands of years of travel time for the wave across a large region of a galaxy. The third small unlock rests in why ringdown is so informative. The late signal depends mostly on the final black hole, not on the messy details of how it formed. The remnant has only a few properties that matter at large scales. Mass sets the overall size. Spin sets the degree of flattening and the frame dragging close in. Frame dragging means spinning mass twists nearby spacetime. The definition stays short. The image stays calm. A slow whirlpool can tug nearby leaves into a gentle turn, even if they stay at the surface. This matters because twisting changes the frequencies of the quasi-normal modes. The wavetone becomes a fingerprint. The main visual anchor shifts outward to the wavefront, leaving the source. The wave is now less tightly packed than at peak. The crest spreads slightly in time. The amplitude drops. The shells become smoother and more symmetric. Each shell has a soft leading edge and a soft trailing edge. The alternation between stretch and squeeze remains. The pattern is now simpler. It resembles a clean set of fading rings that broaden as they travel. The fourth small unlock appears in what cannot be known perfectly. Measuring ringdown requires clarity in the late part of the signal. The late signal is weaker than the peak. It can be buried under other disturbances. This is a limit of observation. It is set by sensitivity and by the presence of other overlapping signals. It is also a limit of inference. Different combinations of mass and spin can produce similar decay if only a short segment is usable. The uncertainty is specific. It lies in separating multiple modes and in resolving small differences in frequency. If the remnant is spinning strongly, the modes can be close together. Distinguishing them demands high precision. The boundary remains gentle. Even if only the dominant mode is seen, it still constrains the remnant's properties. The fifth small unlock returns to the system after the waves pass. The remnant black hole remains. It is larger than either original horizon. It is smoother. The surrounding region becomes calm again. Any leftover gas far away continues its slow orbit. The broken ring of gas becomes an ellipse. Its inner edge remains slightly cleared. The clearance is a physical memory of the binary that was there. Dust grains drift and collide softly. Their distribution evolves over long times. The remnant sits at the centre like a quiet anchor. The scale shift settles outward. The ringdown is a fraction of a second. The dust ring can persist for millions of years. The wavefront that carried the ringdown can traverse interstellar space for thousands of years. Across that travel, the wave remains a pattern in distances. It does not scatter like light. It does not absorb like heat. It fades mostly by spreading over a larger sphere. The section eases toward the next step. A single event leaves a wave pattern that can be recognized far away as a sequence, in spiral, merger, ringdown. The next section moves into how such patterns are separated from background and how a short signal becomes a measurement of distant mass and motion. A brief wave can travel for ages and still carry the same quiet story. The shape of a gravitational wave encodes the masses in the orbit, because the timing of the chirp is set by gravity alone. At this distance, the wave is no longer a nearby disturbance. It is a faint expanding pattern spread across a vast sphere. The first small unlock arrives at once. The information is not in brightness. It is in rhythm, and in the way that rhythm changes. A slow rise suggests a wide early orbit. A faster rise suggests a tighter one. The steady sweep of phase ties the whole arc together. The main visual anchor is a sparse cloud of dust grains drifting in interstellar darkness. 2 grains float far apart. The wavefront passes. For a moment the separation between the grains stretches slightly. Then it squeezes slightly. The change is tiny. It leaves no mark after the wave has passed. Yet the alternation has a clear order. Stretch follows squeeze. Squeeze follows stretch. The wavefront moves on like a soft tide in geometry. The physical detail is the pattern of alternating bands. Each band has a leading boundary where spacing grows. Each band has a trailing boundary where spacing shrinks. The boundaries are smooth and wide. The second small unlock comes from a term used once. Strain is the fractional change in distance caused by the wave. The definition stays short. It is a change divided by the original separation. The example stays grounded. A long rope pulled a little longer changes by a small fraction of its length. The rope returns when the pull ends. In space there is no rope. The distance itself changes by a fraction. This matters because the same fractional pattern can cross empty regions without needing any material support. The narration moves through checkpoints along the wave's journey. First, the wave is strong near the source. The shells are tightly spaced. Second, the wave spreads outward. The same energy is shared over a larger sphere. The amplitude weakens. Third, the wave reaches regions filled with gas and dust. It passes through almost unchanged because interaction is negligible. Fourth, the wave continues into intergalactic space where matter is even thinner. The wave remains a pattern in geometry. The third small unlock rests in how the chirp acts like a clock. The early part changes slowly. That slow change constrains the mass scale because heavier systems evolve more slowly at the same frequency. The later part changes quickly. That quick change constrains how close the orbit becomes before merger. The waveform is a single connected curve in time. Its slope carries meaning. Its curvature carries meaning. The story remains calm because it is repetitive and smooth. A single number can anchor the vastness. The source can lie at about 1 billion light years. That is like crossing the Milky Way about 10,000 times. The number is only a scale marker. It places the travel in a realm where ordinary distances no longer help. The scale shift is gentle. A change lasting 1/10 of a second near the source becomes a wave that travels for 1 billion years through mostly empty space. The event is brief. The journey is long. The main visual anchor shifts from dust grains to a wide view of galaxies as faint smudges. The wavefront crosses the space between them. Nothing visibly bends. Nothing lights up. The wave carries on. The fourth small unlock comes from the idea of a template. The waveform has a characteristic rise. Many possible systems produce slightly different rises. A library of possible shapes can be imagined as a set of quiet tracks. One track fits one mass pair. Another track fits another. This is not a human activity here. It is simply the idea that form can be matched to form. The match is guided by phase coherence. Coherence means the crests line up over many cycles. The definition stays short. The image stays natural. 2 sets of ripples on a pond can align when their spacing and timing match. When they do not align, they drift out of step. This matters because a long coherent segment carries more information than a short loud burst. The narration holds a clear limit of inference. Different combinations of properties can mimic each other. A heavier system farther away can resemble a lighter system closer by. Spin can shift phases and imitate a small change in mass ratio. Eccentricity can add extra tones and resemble spin effects over a short window. This is a specific limit. It comes from degeneracy in the waveform. It comes from the fact that only a finite segment of the signal can be cleanly separated from other influences. Another limit is set by superposition. Many binaries across the universe radiate at once. Their waves overlap. The overlap can form a faint background hum. That background can obscure weaker individual chirps in principle. The boundary remains gentle. The strongest chirps still stand out because their frequency rises in a distinctive way. The fifth small unlock appears in how distance enters the wave. The waveform amplitude weakens with distance, yet the phase evolution does not depend on distance in the same way. Timing carries intrinsic information. Amplitude carries extrinsic scaling. When both are available, a distance scale can be inferred. The inference is not perfect. Orientation matters. A binary viewed edge-on produces different pattern than one viewed face-on. Polarization matters too. Those differences can trade places with distance in the observed shape. This is another specific limit. It is a limit of separating geometry of source from geometry of propagation. The main visual anchor returns to the two dust grains. The wave passes again in imagination now as a train of many cycles. The grains drift. The banded stretch and squeeze arrives. The grains separate slightly, then return, then draw slightly closer, then return. The effect is too small to disturb their slow drift. Yet the pattern in time remains regular. The small scale of the strain contrasts with the enormous scale of travel. The scale shift settles outward once more. A change that is smaller than any grain of dust can still carry across 1 billion light-years as a coherent rhythm. The section eases toward the next step without introducing a new mystery. The waveform is now understood as a message written in timing and phase. The next section moves into what a population of such events implies for the history of massive stars and the quiet architecture of galaxies over cosmic time. A single merger is brief, yet many mergers across time sketch a quiet map of how heavy stars live and end. A population of gravitational wave events reveals where massive binaries form and how often they survive long enough to merge. In that region, each event is a faint ripple. Together the events become a slow census of invisible systems. The first small unlock is immediate. The rate of mergers is not just a number. It is a clue about environments that make close pairs. Dense star fields can reshape orbits. Metal-poor gas can change how massive stars lose mass. Those conditions affect whether two black holes end up close. The story stays calm because it is a matter of probabilities spread across galaxies. The main visual anchor is a broad spiral galaxy seen edge-on. Its disk is a thin, luminous band of stars. A darker dust lane runs along the midplane. The lane is layered. It has ragged edges and pockets of thicker shading. Above and below the disk, a faint halo of old stars extends outward. Within the disk, heavy stars form in clumps. The clumps are embedded in dusty knots. The physical detail is the layered dust lane and the gradient from dense midplane to thin halo. The second small unlock comes from a term used once. Metallicity is the fraction of material heavier than helium in gas. The definition stays short. The example stays grounded. Cleaner gas makes weaker winds in massive stars. Stronger winds peel away mass and widen binaries. Weaker winds let stars retain mass and stay tighter. This matters because it changes how often two black holes can remain bound and close enough to merge within the age of the universe. The narration moves through checkpoints of formation. First, two massive stars form in the same dense cloud. Second, each evolves and collapses, leaving a black hole. Third, the binary must survive those changes without being disrupted. Fourth, the orbit must shrink over time until gravitational waves dominate. Each checkpoint filters the population. A third small unlock arrives in how environments assist. In crowded regions, close encounters with other stars can exchange partners or harden binaries. Hardening means the orbit shrinks through gravitational interactions. The definition stays short. The image stays gentle. Two pebbles in a shallow stream can be nudged closer by repeated small swirls. The stream is not a star cluster, but the idea of many small perturbations accumulating is similar. This matters because a binary that would otherwise remain wide can be tightened by its surroundings. the main visual anchor shifts within the galaxy to a globular cluster. It is a dense sphere of stars. The density rises toward the center. The outer edge fades into the halo. The center is crowded. Orbits in such a place are complex. Binaries pass near other stars more often. The physical detail is the gradient in star density from edge to core. The fourth small unlock arrives with a single number as a calm anchor. Over cosmic time, the observable universe contains on the order of 100 billion galaxies. That is like counting grains of sand across many long beaches. The number is a scale marker. It shows why even rare events can happen often somewhere. The scale shift is soothing. One merger lasts a fraction of a second at peak. The conditions that create it unfold over millions of years. Across billions of years, countless galaxies repeat those conditions in varied ways. The story becomes statistical without losing imagery. The wave events sample different environments. Some come from dense clusters. Some come from quiet galactic disks. Some come from small galaxies with cleaner gas. Some come from massive galaxies with richer gas. The distribution of masses and spins can hint at these origins. The hint remains gentle and imperfect. The fifth small unlock is a limit of inference that stays specific. A wave signal carries mass and spin information, but it rarely carries a clear location inside a galaxy. The wave is an expanding sphere. It does not point sharply back to a small region by itself. There is a limit of localization and a limit of association. Many galaxies can lie within the uncertain region of origin. Even when a rough distance is inferred, many candidates remain. This boundary is set by the weakness of the strain and the short duration of many signals. It is also set by degeneracies between distance and orientation. The population story must therefore be built from many events rather than one. Trends emerge only when numbers accumulate. The narration keeps the calm. The events are like droplets falling over a wide landscape. One drop reveals little. Many drops reveal where the ground is tilted. The analogy is new. It is different from the earlier rope bowl and pond. It is an everyday image of accumulation. It matters because each additional chirp tightens constraints on formation models. The main visual anchor returns to the edge on galaxy. The dust lane is still. The halo is faint. The disk rotates slowly over long spans. Inside the disk, heavy stars appear and vanish in time. The wave events do not disturb the galaxy's shape. They are too small in amplitude at large scales, yet they carry away energy from individual binaries and end those systems. Across the galaxy, the tally of such endings shapes the distribution of black hole masses. It also shapes how often black holes remain in pairs. Some remnants receive a recoil from asymmetric wave emission. Recoil is a kick in velocity from uneven radiation. The definition stays short. The example stays grounded. A canoe can drift sideways if paddles push more on one side than the other. The canoe is not the black hole, but the idea of imbalance leading to drift is close. This matters because a kicked remnant can move within its galaxy, or even escape a small cluster. The physical detail can remain in motion and gradient. In a cluster, the escape speed is lower near the edge. In a massive galaxy, the potential well is deeper. Those gradients affect retention. The scale shift settles outward again. A small asymmetry during a fraction of a second can change a remnant's path for billions of years. The section eases toward the next step without opening a new mystery. The population view now feels like a quiet atlas made of rhythms. The next section moves into consequences across cosmic time, and the soft perspective that comes from seeing these events as part of a long repeating pattern in the universe. Across long time, the universe does not only expand and cool, it also rearranges its dark compact remnants into new patterns. A history of binary black hole mergers becomes a quiet record of cosmic evolution. In that region, the record is written in timing and in distributions rather than in light. The first small unlock is immediate. Gravitational waves offer a way to trace massive star remnants even when no glow appears. The waves sample different eras. They arrive now from events that happened long ago. The sky becomes a layered timeline. The main visual anchor is a deep view of the universe as a field of faint galaxies. Some are large spirals with thin disks, some are small irregular smudges. Between them is a soft darkness with occasional filaments of faint gas. The physical detail is the filamentary structure. It forms gentle strands and nodes. The density changes gradually along each strand. At the nodes, the density is higher. Galaxies cluster there. The second small unlock comes from one term used once. Look-back time is how far into the past a signal originates. The definition stays short. It is the travel time of the signal to the present. The example stays calm. A distant mountain appears as it was when its light left it. A distant merger is heard as it was when its waves left it. This matters because events at different distances probe different stages of the universe. The narration moves through checkpoints of cosmic environment. Early on, gas is cleaner. Heavy stars can retain more mass. Their remnants can be heavier black holes. Later on, gas is enriched by many generations of stars. Winds in massive stars can be stronger. Remnants can be lighter on average. These are broad tendencies. They are not rigid rules. The third small unlock is a gentle scale connection. When a distribution of masses shifts with distance, it can imply a shift in the underlying stellar environments. The wave events become samples along the look-back axis. The samples accumulate slowly. Each event adds 1 point to the map. The map becomes clearer as points gather. A single number can anchor the oldest portion of the story. The age of the universe is about 14 billion years. That is like stacking 14 billion single-year rings in a tree trunk, but the trunk is the cosmos itself. The scale shift is soft. A merger lasts less than a second at peak. Its waves can travel for billions of years. When they arrive, they carry the short rhythm intact. The fourth small unlock comes from how expansion affects the signal. The universe stretches space on large scales. That stretching also stretches the wavelength of the wave. The frequency received can be lower than the frequency emitted. The word can stay plain. The signal is redshifted in time. The definition can stay short. Redshift means the wave period is stretched by expansion. The analogy is new and everyday. A slow-moving conveyor belt can spread evenly spaced marks farther apart as they travel. The marks remain in order. Their spacing increases. This matters because the observed chirp can appear slower for distant events. Interpreting the masses then requires accounting for that stretch. The main visual anchor shifts to a long filament between galaxy groups. The filament is tenuous. It has a gradient in density. Near the nodes, gas is thicker. Farther along it thins. The wavefront passes through the filament. It does not bend or scatter appreciably. Yet the expansion of the universe sets the overall scale on which the wave travels. The fifth small unlock is a limit that stays specific. Redshift affects the observed waveform. Distance and redshift are linked. Yet converting observed redshift into distance requires a cosmological model. That model has parameters. Those parameters have uncertainty. This is a limit of inference. It is not a failure of the waveform itself. It is a boundary set by how expansion history is known. Another limit comes from selection effects. Only the stronger events are seen more easily at greater distance. This bias can skew the apparent population. A population can look heavier at distance partly because heavier events are louder. This is a specific observational limit. It arises from detection thresholds and from the steep drop in amplitude with distance. The narration keeps the calm by treating these as gentle corrections rather than dramatic obstacles. The sixth small unlock is how the same measurements can turn the problem around. If distances and redshifts can be associated statistically, the wave events can help constrain expansion. Even without bright light, a population can act as a kind of standard measure. The term can remain plain. A standard siren is a distance indicator from gravitational waves. The definition stays short. It uses waveform amplitude and phase evolution to infer distance. The analogy stays everyday and new. The pitch and loudness of a distant waterfall can suggest how far it is when the source behavior is known. The waterfall image is not perfect. It still helps with the idea that signal properties can indicate distance. This matters because waves can add a new line of evidence about cosmic scale. The main visual anchor returns to the deep field of galaxies. The field is quiet. The filamentary web remains faint. Over long spans, galaxies drift along the web toward nodes. Mergers occur within galaxies and within clusters. Each merger sends waves across the web. Those waves do not reshape the web. They simply cross it. The physical detail returns to gradients and layering. The web has thicker nodes. The galaxies have layered disks and halos. The waves travel across those layers without caring about composition. The scale shift settles once more. A dense region within a galaxy is small compared with a filament between clusters. A filament is small compared with the observable universe. Yet a single waveform can cross all those scales while preserving its phase. The section eases toward the last step without opening a new mystery. The cosmic record now feels like a slow archive of brief events. The final section moves into a gentle resolution. It gathers the arc from two giant stars to a measurable signal and lets the mind rest in the steady rhythm of scale and time. A merger fades quickly, yet its pattern remains like a gentle imprint in the fabric of space. The final collision leaves a stable black hole and a departing train of gravitational waves that carries a complete summary of the last moments. In that region, the summary is not written in light or heat. It is written in timing, in phase, and in the smooth decay that follows. The first small unlock arrives at once. The loudest part of a signal is not the whole story. The quiet tail matters. A final vibration settles the remnant. The main visual anchor is a dark void bordered by a thin, pale ring of hot gas in a distant system. The ring is not a perfect circle. It is slightly oval. Its brightness has a gradient. One side is brighter where gas is denser. The inner edge is sharper. The outer edge fades softly into darkness. The physical detail is that edge contrast and the smooth fall-off of brightness. The narration moves to the moment after the merger. Two horizons become one horizon. The joined boundary is smooth in the sense of geometry, yet the surrounding space-time is still in motion. That motion is not a ripple on a surface. It is a changing curvature in the space around the remnant. The second small unlock comes from a single term used once. Ringdown is the final settling of space-time after a merger. The definition stays short. The example stays calm. A struck bell does not keep its first shape of vibration. It relaxes into a simpler pattern and then silence. This matters because the ringdown frequency and decay depend on the remnant's mass and spin. The story remains gentle because the details are smooth. The waveform is a curve that rises and falls. It does not explode. It does not shatter. It turns from fast oscillations into slower ones. Then it fades. The main visual anchor shifts within that distant system. The thin ring of gas shows a shadowed interior. The shadow is not a hole in gas. It is a region where light paths curve away. At this distance, the shadow has a soft boundary rather than a crisp line. Scattered photons add a faint haze. The haze is layered. It is brighter near the ring and dimmer toward the centre. The third small unlock is a calm link between the wave and the shadow. Both arise from the same curvature. The wave shows how curvature changes in time. The shadow shows how curvature bends paths in space. They are different windows into one structure. The narration returns to the journey that began with two giant stars. A pair forms in a dense cloud. Their lives are brief on cosmic scales. Their cores collapse. Their remnants orbit in darkness. Over long spans, the orbit shrinks. The shrinking is slow at first. It becomes faster near the end. The fourth small unlock comes from the simplest reason for the shrink. Gravitational waves carry energy away from the orbit. They also carry angular momentum away. The orbit cannot keep the same size without those quantities. The loss is continuous. It has no pause. The everyday analogy stays new and quiet. Snow on a branch settles downward over time. The settling can be almost imperceptible at first. Then a small shift can make the branch relax into a lower curve. This matters because Inspiral is a long settling followed by a short final change. The section holds to two main concepts. Energy loss through waves is one, ringdown is the other. A third concept appears only as plain language. Curvature is the background that makes both possible. A single number anchors the scale without crowding the mind. Near the last moments, the separation can be about 300 kilometers. That is similar to the length of a wide canyon carved into bedrock. The scale shift is gentle. This canyon-sized gap exists around objects that outweigh stars. The time to cross that gap at light speed is a blink. The time that leads to that gap can be billions of years. The fifth small unlock comes from how the signal encodes mass. The chirp accelerates because the orbit tightens. The chirp rate reveals how heavy the system is in a combined way. When the combined mass is larger, the late Inspiral tends to occur at lower frequencies. The ringdown then follows with its own characteristic pitch. Together they form a consistent picture. The section includes a soft limit of observation that stays specific. There is no direct image of the orbit itself in most cases. The inference comes from matched patterns. Many combinations of distance and orientation can produce similar amplitudes. Noise can mimic small parts of a waveform. This is a limit of parameter estimation. It is also a limit of localization. A sky region can remain broad. The event can be associated with many possible host galaxies. The boundary is not dramatic. It simply means that certainty grows with many events and with careful modelling. The narration keeps the calm by returning to physical shape. A gravitational wave is a stretching and squeezing that alternates. The stretching is not measured as a ruler length in space. It is a fractional strain. The strain is tiny at great distances, yet the phase coherence can remain. The curve stays in step. The sixth small unlock is that coherence itself. A wave that travelled for billions of years can arrive with a pattern still intact. The universe is not perfectly smooth. It has filaments and clusters. It has voids. Yet the wave is not easily scattered. It passes through changing density with little alteration. It is a messenger of motion rather than of light. The main visual anchor returns to the ring and shadow. The ring is steady. The inner shadow remains dark. The gradient stays smooth. The system rotates on a timescale far longer than the wave event. The merger that formed the remnant is already done. The remnant continues as a quiet geometry. The seventh small unlock is a soft closure of the arc. The story begins with two giant stars that never meet directly. It ends with one horizon that holds the combined mass. The waves are the bridge. They connect a long evolution to a short finale. They connect invisible objects to measurable patterns. They connect small time spans to cosmic history. The section keeps one last scale shift. A single second can contain the loudest emission. The conditions behind it can span millions of years. The broader population can span the age of the universe. The mind can rest in that layered timing. The last analogy remains unique and gentle. A long-dune field can store the history of many winds. One gust makes a small ridge. Many gusts shape a smooth slope. This matters because one waveform is a ridge. Many waveforms become a landscape of understanding. The ending remains soft. No new mystery opens. The universe continues to expand. Black holes continue to form and merge. The waves continue to travel outward. In that wide quiet, the final image stays simple. A dark center, a thin ring, a fading ripple that becomes stillness.